So the idea here for non-associative plasticity is very simple. Experimental evidence shows very clearly that for many materials, the response is significantly non-associative in terms of the flow. Okay, here we mean plastic flow. So what does it mean? So what people do is, they experimentalists go in the lab and they map the elastic region for a given material: steel, rock, concrete, plastic, whatever you want. Okay, and so you can get this bound, you can get this yield surface. Okay, and as we have seen, this surface has certain geometrical characteristics, like it has a certain normal that we've been calling n hat, right? And that's normal to the yield surface. Now, our plastic flow rule, essentially so far has been telling us that every plastic strain, or every increment in plastic strain, is always parallel to that normal. Right? That has always been the case. This has been always df d sigma, okay, in every model that we've got so far. Now, experimental evidence shows that in reality, this epsilon dot p is typically not aligned with n hat. Okay, it means that there is an angle here, theta, okay, and theta is typically not equal to 0, that divides, if you will, or separates n hat from the true plastic strain rate. Okay, so that means, so this is f equal to 0, that means that I want something that, well, okay, let's say that, let's put it this way, that epsilon dot p is typically not parallel to df d sigma, which is equal to n hat. Okay? In other words, writing the associative flow rule is not accurate. Okay, from a phenomenological point, okay, not from a theoretical point, simply from experimental observation. Okay, and again, if you look through the literature, you find it. Okay, there's people plot the plastic strain rate or the plastic strain increment, and you can see with your own eyes that it's just not normal to the yield surface. Okay, so what people do is they postulate, and engineers do this very well, that there exists a certain function Q that we're going to call the plastic potential, such that I can write my flow rule to be the same plastic multiplier as before, but with the only difference that now the direction of the plastic strain rate is given in terms of the normal to that other surface. So if I come back here to my graph, I'm going to have at this point, I'm going to have another surface here, right, whose normal to it is a plastic strain rate, right, so that I can satisfy this. Obviously, when Q equals F, I have the associative plasticity case, again, as I've been having so far. But when Q is not equal to F, when Q is another function, then I have this more general. Okay. Another way to see it in a very pragmatic way is that you introduce a new degree of freedom in your formulation. Right? You have one more variable, one more set of parameters to play with, and that obviously will always increase accuracy. Right? The more knobs you have in a model, the better off you're going to be. Right? It's funny because sometimes I review papers, and the authors write very proud, and say, "Oh, we've shown that the model is more accurate than its predecessors." Yeah, of course, it has 10 more variables. It has to be more accurate. Okay. Also, so far we have been saying that hardening is constant. That's not always the case. So hardening in complex materials, read here most engineering materials, is usually non-linear. Okay? And it needs to be obtained or calibrated experimentally. So back in the 60s, 70s, and even after the 80s, this was a big deal. Okay? People were in labs getting F, getting Q, getting hardening moduli fluctuations. You still see, every now and then I go to the National Science Foundation every year to serve on a panel. You still see some guy somewhere proposing a new plasticity model, okay? But those guys are not getting funded anymore, okay? It's over. Okay, so if you wanted to devote your career to developing a new plasticity model, I suggest that you look for something else because it's over, okay? It's fairly saturated. Nobody's getting funded for this, okay? So, which is a pity because the models that we have are not perfect, but the whole fever of constitutive modeling is over, okay? So what we do here is we define, so this is a definition, a kappa that is different to the one we had before. Remember, we had a kappa in our yield surface. Now we're going to generalize this kappa and call it the vector kappa, okay, which is a stress-like vector of plastic internal variables. These famous PIVs that we have been talking about. For example, right, in the J2 model, which is the only model that we've seen, kappa is a scalar for isotropic hardening, right? And kappa is equal to alpha. Is it alpha or alpha? Alpha, but in vectorized form. For the kinematic hardening model. Right? So I can always store my plastic internal variables in this kappa, the vector, in a vectorized form. So in the case of the isotropic modeling, kappa is just a radius of a yield surface, it's a scalar. In the case of the kinematic hardening, it's a second order tensor, but it's a symmetric second order tensor. I can always pack it in a vector. Even if it's not symmetric, I can always pack it in a vector, right? Using Voigt notation or something like that, right? You can always take your components and just put them in a vector array, right? If it's symmetric, it's going to be a 6x1. If it's not symmetric, it's going to be a 9x1, right? But it's no big deal, okay? Now, you can generalize kappa further, even in the case of the generalized hardening for J2, where the first entry of kappa the vector is kappa the scalar. and then the subsequent entries are the alphas, okay? In other words, you can always pack all of your plastic internal variables, everything that is changing in your plasticity model into this vector of stress-like plastic internal variables. Is that clear? Okay? You can always do that for any model. And then consistency, F dot, okay, will require that we evaluate F dot with respect to sigma as usual, but now with respect to this kappa wiggle in general. So by the chain rule, F dot implies df d sigma double contracted with sigma dot as usual, plus df d kappa the vector dotted with the variation of kappa, and that has to be 0.
I have a question.
Yes, sir.
When we write the equation for the yield surface for kinematic hardening, I believe it is the norm of S or C rather than minus alpha minus kappa.
Mm-hmm.
And you said in this case that the kappa vector can be looked at as being alpha.
Right.
What about that other kappa that remains?
That other kappa is a constant, remember?
Right.
In the kinematic. In the purely kinematic model, right, that kappa is a constant. So if this makes you uncomfortable, change it, give it another name so that it's more, maybe we should call these guys, I don't know, P or whatever. Okay, so then P, replace it here, df dp, P dot. And then the entries of P in the case of the kinematic model is alpha, right? Kappa doesn't change. It's not really a plastic internal variable in the purely kinematic model, right? In the purely isotropic model, it is.
Yeah.
And then in the combined one, both of them are here. You see that? Okay. All right. So, right. What am I doing? Right. So then I can open this up and say, okay, this is df d kappa dotted d kappa d lambda, okay, the variation of kappa with respect to the plastic strain times lambda dot. Okay, I'm just further decomposing things. All right, and these we have rather arbitrarily called it before H lambda dot. Okay, with a minus in front of it. It's a name. It's something that we have chosen to do. Okay, and therefore this gives us a definition for H. So the hardening modulus, whether it's constant or variable, it always is equal to minus the variation of F with respect to kappa times the variation of kappa with respect to lambda, or if it makes you feel better, sometimes I look at it like this, it's just the variation of F with respect to lambda. That's really what it is. But it's good to remind yourself of this form because this emphasizes that what's really changing through lambda is this plastic internal variables. Okay, and they induce a change in F. When you look at F in this form, you don't necessarily see the influence of lambda, but if you will, lambda is there. Okay, kappa always depends on lambda. Remember? Plasticity variables are evolving with plastic strength. Okay? So, if you're an experimentalist and you go to the lab and you're trying to come up with a new model, this is what you do. You try to evaluate the change in F due to plasticity. And the way you structure the formulation is through this formalism. Okay, but at the end of the day, you're going to come up with, what they do is they come up with some function here of whatever plastic internal variable you have as a function of lambda. Okay, and that's really this part here. And then they postulate how that plastic internal variable affects your plasticity or your plastic surface, okay, your yield surface. Okay? So, this is what we are going to be calling the generalized hardening modulus. Why? Because it doesn't assume necessarily that H is constant or anything like that. It can be any. So in the isotropic case, so just to, in J2 isotropic, right, what do we have? dF d kappa, the scalar, is equal to minus 1. Is that right? Remember that in the isotropic model we have F equals L2 normal S minus kappa equals 0, right? So dF d kappa minus 1, right? And then d kappa d lambda, right? What did we say that is? What is it in this case? What do you think it is going to be? It's H, right? It's our good old friend H, the constant. Okay? So your generalized hardening modulus is your constant H in the isotropic model. Okay? In the kinematic model, let's see, now this time let's see if you can deduct it. F equals this C guy minus kappa, but that's not very useful. This is really S minus alpha minus kappa equals 0. Okay? Now, dF, what I'm really looking at is, what's the first derivative, really? What is dF d kappa, the vector in this case? What should it be? Oh, what?
Alpha.
Right, dF d alpha okay, that's G. That's not very nice. Let's see. Something like n hat. Maybe I should look at my notes. Yeah, minus n hat. Okay. And then d alpha d lambda in this particular case, or we've been calling it really here like this, we've been calling it alpha dot. Okay, we know by the hardening rule that we postulated that is this. Okay, and right, okay. So, if you will, your D, if you want to see it like this, your D alpha D lambda is simply H and hat. If that helps you visualize it a little better. So again, when you multiply everything through, when you multiply this, you dot it with this, you get the n hats go, and all you get is H again. Your generalized modulus is H again. Okay. And these are the vectorized ones. These are the vector form of n hat. Okay, why? Because remember we vectorized kappa. So this guy has to be a vector. It's not it's not a second order tensor. Okay. So like 6 by 1, whatever it is. Okay?
In general, what's the advantage to vectorizing everything versus keeping it as a tensor?
I think it's an old consequence of Fortran codes, you know, when the void notation was really important when we were coding these things at Fortran. Now with more advanced coding languages, I don't think I haven't looked at say C++ codes of finite elements or even MATLAB codes, but I would imagine that they don't vectorize. I must say though that a lot of people still run Fortran in vectorized forms because it's just fast. I mean, it's very good. But yeah, it's an inheritance from the times of void notation. Okay. Let's see. So okay. Also, sigma dot equals CE double contracted with epsilon dot E. And therefore, this is CE double contracted with epsilon dot minus CE double contracted with epsilon dot P. That's all very good. And now, given our new concept, this is CE double contracted with epsilon dot minus lambda dot, if you will, CE double contracted with, and I of course run out of space. Let's write it here. This is the same. You get a lambda dot CE double contracted with dq d sigma. Okay, because now we're using the non-associative flow, right? So it's dq d sigma. Okay, so this is my variation of sigma, and okay, we adopt some short notation. We let little q be dq d sigma, so the normal to the plastic potential, and we let in general little f be df d sigma. Okay, sometimes little f will be just n hat, whatever it has to be, but in general we just call it little f. Okay, there are models where it's not n hat. Okay, so now we're ready to go. So again, we go back to the f dot equation, which is here. Okay, so we get little f, which is df d sigma, double contracted with sigma dot. I just plug in this guy, right? So I get CE double contracted with epsilon dot minus lambda dot CE double contracted with little q. So all of this is just sigma dot, right? Minus h lambda dot. Has to go. I collect my lambda dot terms, so I get lambda dot times, the h is going to have a minus, right? So, okay, and I'm going to send it to the right hand side. So I get lambda dot h plus little f double contracted with CE double contracted with q. So the scalar, okay? Fourth order tensor double contracted with a second order tensor and then further double contracted with the second order tensor. This is a scalar product. Okay. That whole thing has to be equal to little f double contracted with CE double contracted with epsilon dot. So this is already telling you that lambda dot is going to be proportional to some projection of your total strain rate, right, onto the elasticity and onto the normal of the yield surface, okay, whatever that projection means, all right? And then further scaled by whatever this is, okay? So lambda dot equals 1 over h plus little f contracted with C contracted with Q times this guy. So these two things are scalars, and I'm just writing them like this to emphasize that. Okay, this is a scalar, that's a scalar. And then sometimes you see people give this guy a special name, chi. Okay, so people say lambda dot equals 1 over chi little f CE epsilon dot, where chi is nothing but your hardening modules plus whatever this is. So let's do a calculation real quick. In the J2 model, what's little f? Quickly. N hat. C is C, what's Q? N hat, right? So here you get N hat double contracted with C that gave us 2 mu N hat. 2 mu N hat double contracted with N hat is just 2 mu. 2 mu plus H chi, right? Remember we got that last time. F again is N hat double contracted with C, 2 mu N hat. So we got 2 mu N hat double contracted with epsilon dot. And did we get anything special out of that? No, right? That was just what it was in the numerator. Now, when H was equal to 0, when we had perfect plasticity, those 2 mu's canceled each other out, right? And we got that lambda dot was equal to the projection of epsilon dot onto N hat, remember? So it was N hat double contracted with epsilon dot. Okay, so everything fits back into place, okay? But this is the general form for the plastic multiplier for every model that has the structure that we have postulated. And it just turns out that 95% of the models follow that structure. Okay, every now and then you'll find a model that doesn't follow that structure. It'll annoy the hell out of you. Okay, because the structure is very nice, it's very compact. Questions so far?
Can you explain why the letter Q is in hat?
Because we have, in the model we've been studying, is everything is associative. So little q is df d sigma, which is n hat. Right? In the J2 model we've been looking at, everything is associative. Q is equal to n.
Oh, okay.
Right. All right, so now, as usual, we go back full circle, we come here. In fact, let's do it on a new board. So, let's see. So sigma dot is CE double contracted with epsilon dot, and then there's a correction, right? Lambda dot, which is 1 over chi little f CE epsilon dot, and then I have CE double contracted with little q. Right? All I'm doing is rewriting this and making use of the fact, oh, I'm actually, oh yeah, I'm here. Right? Everybody see that? I'm just rewriting sigma dot with the newly found information about lambda dot. So this is lambda dot. Scalar. CE fourth order tensor double contracted with a second order tensor, you get a second order tensor out of this. So this is my magnitude, this is my direction, and that's going to correct this guy. All right, now I play a little game with additional notation. So let's do it here aside. F double contracted with CE double contracted with Q can be written as Fij CE IJKL QKL. 1 over chi doesn't matter because it's a scalar. And then I look at this. CE double contracted with Q gives me something that is like CE, let's say, MNRT QRT. Right? So the free indices in sigma dot would be what, given what I have written here? Mn. That's right. So that's the only thing I need to keep in mind, that this guy is the one that gives me my free indices. Now, let's see. What do I want to do? No, you guys are letting me do whatever I want. This is not what I want. This is this guy, right? That's why it didn't make sense. Right? Okay. Now I can play the game I wanted to play. So this is my free index. This guy contracts with that guy. This guy contracts with this guy. Right, so now I can rewrite 1 over chi F double contracted with CE double contracted with epsilon dot times CE double contracted with Q. I can rewrite these as, so let's call these, let's give it a name. Let's call it P. Okay, P is a second order tensor, right? Okay, whatever this is. So P Ij equals 1 over chi, that's just a scalar, F M N C E M N R T epsilon R T dot. And then so this is a scalar, doesn't matter. Everything is a dummy index here. And then I write C E I J K L Q K L. You still with me? Right? So my free indices are these. Those are the only two that matter. And they're the ones that give P its free indices. Or in this case, they have to be the same as sigma dot. Now I can rearrange things. Check it out. So this guy will always have to stay together, right? Because they are contracting. But I can move this, for instance, to the front and not change anything because this is a scalar. Right? And furthermore, I can rearrange things as follows. I can say So check this out. Pij equals 1 over chi, so I want to get chi out so it doesn't bother me. Cij KL, K or Q KL, F MN, CE MN RT, epsilon RT, epsilon dot. Haven't changed a thing. Okay? Everybody gets contracted, this guy gets contracted, these two guys get contracted here, these two guys get contracted here, and these two guys get contracted here. And the only one that has free indices is this guy. Okay? Now I write it in direct notation. P equals 1 over chi. Right? This is C. CE, the fourth order tensor, double contracted with Q. Right? That's what this operation means. Okay? Then I'm going to have to write an F, double contracted with CE, and that CE is also double contracted with epsilon dot, correct? And now what happens in between these two guys? What's the only operation that makes sense? Dyadic product, right? They don't share, they don't have same indices. Okay, so the only product that you can have here, you're multiplying things. The only product that you can have there is a dyadic. All right, so check this out. So these two guys together, that's another way to see it, make a fourth order tensor. That fourth order tensor is double contracted with another fourth order tensor. So that gives you these two guys, when you hit them together, this gives you a what kind of tensor?
Scalar.
No. Only two indices are contracting, right? So this is a fourth order tensor. That's contracting with a fourth order tensor, but only in two indices. So what do you get? You get a fourth order tensor, right? With three indices, Mn, Ij. That fourth order tensor is double contracting another fourth order tensor. So again, when you do the whole contraction, everybody here in the parentheses, that is a fourth order tensor of indices now Ij, Rt. Call it whatever. A. Okay, indices I, J, RT. A, I, J, RT is being contracted with epsilon dot RT. So it's a fourth order tensor double contracting a second order tensor, gives me back a second order tensor with indices that give its indices to P. Now, so this A is very similar to the CE, essentially. I mean, it's a fourth order tensor. I mean, it's more complicated, but it's the same thing. So I can rewrite the whole thing now as sigma dot equals CE double contracted with epsilon dot, and if you will, something that looks like 1 over chi A double contracted with epsilon dot. Okay, so this is CE minus 1 over chi A, all of that double contracted with epsilon dot. Okay, and if I just expand A is only here to help us visualize. It's really, what did we say it was? CE double contracting little f, no, Q, diet F, CE, all of that double contracts epsilon dot. So meet your new friend, CEP, which is CE minus 1 over chi CE double contracted with Q, diet F, double contracted with C. Right? This is your canonical elastoplastic modules. So that sigma dot equals CEP double contracted with epsilon dot. Again, do the test. For the J2 model, this is n hat, double contracted with CE, gives me 2 mu n hat. This guy double contracted with CE, 2 mu n hat. Right? When I multiply the whole thing, I get 4 mu squared n hat diet n hat. Check your CEP. It's down. Okay? Continue. All right? It's the analytical CEP. It's not the one you would use in your calculations in your finite element code. This is the analytical version of the modules. Okay? It doesn't take in, it's a one that comes up in the rate form. It's not the one that relates delta sigma to delta epsilon, which is eventually what you're going to need in your integrator. Okay? So people were using that guy in the finite element codes, and they were not converging fast enough. Right? They were not converging at the rate that Newton-Raphson typically converges, simply because that's not the true rate when you're numerically integrating. Let's see, what do I want to say about this? So let me just make a few notes and then we'll ask questions. So, some observations here. Again, true for pretty much every model that you're going to encounter. So yeah, continue model. Note, when Q not equal to F, meaning when you have a non-associative model, all right, then this destroys the major symmetry of CEP. Remember that a fourth-order tensor has major and minor symmetries? Do you remember that? Right? You can speak of both things. So this means, i.e., right, thatCijkl EP, it's not equal anymore to CEP KL IJ. That symmetry is lost. And you can see it, let's see it here. So, let's look at it here. So, do the indices here. IJKL. This is also IJKL. There's nothing else there. This guy is a scalar, so let's forget about it. This guy is going to be IJ, R, let's say M, N. This guy would be M, N. This guy would be whatever it has to be, RT. And finally, this guy will be RTKL. Right? Major symmetry means that I can swap these two guys, right, with each other. These guys by those guys. Now, when F is equal to Q, I can do it. I can pull it off, right? I simply move this whole term to the front, I move this whole term to the back. No problem. Okay? But now that Q is not equal to F, I can no longer do that. Okay? The order of the products will make a difference. It's not the same to write CE double dotted F diet Q double dotted CE. Not the same. Okay. So you gotta be very careful. In the associative case, it doesn't make a difference because the normal of this and the normal of that are the same. So they can commute. Okay. When this is not equal to that, they no longer commute. Okay. So your major symmetry is gone. So that means that you can no longer pack CEP as a 6 by 6. Okay. You have to pack it as a 9 by 9. Okay. The major symmetry destroys that compactness. And that will impact your CTO. Your consistent tangent operator will also be a 9 by 9. So the second you have a non-associative model, many of the compactness properties that you had in very nice associative models are out the window. That being one of them. Major symmetry is gone. But of course, minor symmetry is still in place. Meaning CEPIJKL is still equal to CEPJIKL, still equal to CEPJILK, still equal to CEPIJLK. The first two and the last two indices still commute. Check it out. This guy has minor symmetry. So the IL, the IJ and the KL commute with each other. This guy, same thing. This guy, same thing. So the minor symmetry of CEP is inherited from the minor symmetries of the CEs. See that? And the plasticity has no business in it. Now, what does that mean? What do you think is a consequence of CEP having minor symmetry? Can you see a consequence, a direct consequence of the minor symmetry of CEP? What would happen, let's put it another way. What happens if we didn't have minor symmetry in CEP? That's right. Your stress increment would no longer be symmetric, right? Because this guy is, let's say, IJ, and this guy is IJ, KL, right? And this guy is KL, so KL doesn't matter, but IJ matters. If you cannot commute I with J, you cannot commute I with J in sigma dot. So sigma dot just lost minor symmetry. It just lost its symmetry if you don't have minor symmetry in C. And what's a violation of symmetry of sigma? Do you remember? What is that tied to in continuum mechanics?
Balance of angular momentum.
Pardon me?
Balance of angular
Right,
momentum.
exactly. So that you would have a violation of angular momentum. So it's all tied together. Now there will be models that will break that symmetry in sigma, and therefore you no longer have balance of angular momentum in the continuum sense, and those are they're more complicated models. So again, you can't anymore pack sigma in a 6 by 1. You will have to pack it in a 9 by 1 because you no longer have symmetry in those models. But in all of the plasticity models, you do have that symmetry still, and that's a nice thing. Questions to this point?
Then it stops being Cauchy stress.
Well, they still call it Cauchy stress, but they call it Caucera continuum.
Ah,
Yeah, it's another type of continuum theory. And I mean, some people like it very much. So there's a whole school of thought that is predicated on Caucera continuum. But I think that life is too short to spend it on Caucera. But that's my point of view. Any questions? Yes, sir.
In the non-associative, is Q typically some type of rotation of F, or is it just in general?
No, we will see. Yeah, we will introduce it. It's a function. It's a surface. Yeah, but yeah, I wouldn't see it as a rotation. I guess you could come up with some rotation of F, but in general, it's just another surface. In fact, it turns out to be, in most models, it's going to be form identical to F, with some parameters slightly different, so that you get the difference. But it's pretty simple. People usually, I mean, what they try to do is come up with a Q that is as close as possible to F, but still enables them to capture that experimental observation that the normal is not truly normal to F. Right? So they essentially get inspiration from F, and they say, okay, how can I tweak F so that I match what I see in the lab? And then they define that as Q. Okay. Anything else? Okay, then let's plow forward. So this is going to be very useful because from now on we want everything is. So at this point, the way I feel is that I feel that we have covered the framework for elastoplasticity. Okay, so everything from this point forward is variations on this framework. Different F, different Q, different H's, and so on, but the form doesn't change, okay? That's why we call it the canonical form, okay? Because it's the same for every model, right? So it's useful to spend some time in getting familiarized with this form and being comfortable with it, because from this point on, we just use the same form over and over again. Nothing changes. Okay. All right. So let's switch topics then and introduce a new type of model. So far, we've spent our time with J2, variations of J2, either being kinematic or isotropic hardening or the combined one. But at the end of the day, our yield surface has been the same. Our yield surface has coincided with our plastic potential, making it an associative model. And we just saw with a quick calculation that we always match this canonical form, even in that case. But many materials are different from the ones that the J2 material or the J2 model attempts to capture. So J2 was born in an attempt to simulate metals, okay? And so that's really where plasticity started. Plasticity was born with metals. And if you look at the original experiments, that's really what the creators of a J2 plasticity model were thinking of. They were thinking metals. And so for metals, you have very nice properties, like the J2 model doesn't have this pressure dependence that we talked about, right? You go along the hydrostatic axis, the response is always the same. That's why you have the cylinder that is centered at the hydrostatic axis, and the radius of the cylinder is constant, okay? So that's a nice property of steel or metals in general. Relatively mild pressure dependence. Another nice property, associativity. Your plastic flow increment is more or less in the deviatory direction always, or normal to the J2 surface, meaning that your plastic strain has pretty much no component in the volumetric direction for metals, okay? For other materials, that's not it's not as easy or as nice, okay? So take the case of concrete, which is the other very popular engineering material. Concrete is very much pressure dependent. Okay? You change the pressure and you change all the properties in concrete, okay? The plastic strain rate in concrete is definitely not normal to the yield surface, and so on. So you have other materials that are of engineering interest that don't match the nice associative, the nice form of a J2. So what people started to do in the 60s and the 70s is they made a business out of coming up with these variations, okay, that fitted other models or other materials. So one of the classic models, it's actually older, but then it got adapted to plasticity, okay? So many of you are probably familiar with the classic Mohr-Coulomb. And I'm going to call it here at the beginning failure criterion. How many of you have seen the Mohr-Coulomb before? The failure criterion. Nobody? You've seen Mohr circles. Okay, good. That's a good start. Okay, so Mohr circles, if you remember what people would call Mohr space, it's in a space tau sigma. Okay, or all right, sometimes you know, you see it in a space sigma, and then this would be like sigma xy, and then you would plot your state of stress. That's what Mohr circle was about, right? It would be these little circles, usually, so two of them, that essentially give you the three-dimensional state of stress. Okay? So that's where the part Mohr comes into the place, okay? Your state of stress will always plot as a circle. So I'm going to have, let's say here, a certain sigma 1, sigma 3, and I'm going to put bars here because I'm going to order them. And I'm going to have a circle here, or the semicircle in tau sigma space. So that's where the term Mohr comes into the piece. So for now, that's Mohr. It tells you a state of stress in a stress space. Now, tau, we define it as the shear stress. And sigma is our normal stress. Typically at a point in space. However, this is where Coulomb comes in. So Coulomb said, you have a point that has a particular state of stress, a material point. That material point will have a failure plane. Okay? Okay? And failure will happen along that plane when the normal stress, sigma, on that plane, or the mean, some people call it the mean normal stress, matches moduli some constant, the shear stress. Or another way to see it is that your shear stress at failure, on that failure plane, will always be proportional to the normal stress. So that gave rise to what people would later call the Coulomb failure envelope, right? That essentially says that there's an angle here, phi, that will relate your sigma and your tau at failure on the failure plane. Okay, so Coulomb essentially did a bunch of tests and came up with a conclusion that invariably these materials were failing on a plane. First of all, there was a failure plane, and then that there was this relationship between the normal and the shear stress at failure. Okay, and he called that, or people call that, the failure envelope. Okay, so let's call this the Coulomb failure envelope. So where does Coulomb and Mohr get together? Gets together in the following way. There is a failure envelope for every material, say concrete, rock, soil, what you wish. And then your material undergoes a certain state of stress that gets mapped onto this Mohr circle. If the Mohr circle is below the failure envelope, your material is happy. No failure, no problem. If the Mohr circle grows to a point that it touches the failure envelope, you got failure. Okay? And then it got even more interesting because it turns out that the circle always meets this envelope at a tangent, meaning that this angle between the radius of a circle and the envelope is always a 90-degree angle. And then people realize that this angle here, what am I calling it? Nothing. Let's call it alpha, is related to this angle. Do you remember what the relationship is?
Yeah.
What is it?
It's pi over 4 plus phi over 2.
So which one's which?
Alpha is equal to pi over 4 plus.
So this is not alpha. No. But
that's 2.
right. No. That's relating these to these.
Mm-hmm.
But in general, this one here on the Mohr circle is like half of this one,
That's 2 alpha. That's alpha.
right? So this is alpha, and this will be 2 alpha,
Mhm.
right? Right, and then there will be a relationship between alpha and this phi, yes, which is, if I'm not mistaken, alpha is, as you said, pi over 2, or pi over 4, pi over 4. So 45 plus phi over 2. So that gave rise to the direction of what people would call failure planes, or shear bands, or cracks, all the kinds of failures that you typically, if you've ever been in a concrete lab, they test these concrete cylinders, they put them under compression, the failure plane when the concrete breaks, that's this, yes sir.
That's 90 minus and not 2 alpha, because 2 alpha would always be obtuse.
I think you're right. So then this one is 2 alpha?
It depends on where you.
I think that,
Yeah.
the large one.
This one is 2 alpha.
Uh-huh.
Yeah,
That's
I think you're right. Okay, let's not pay too much attention to alpha because I don't have it here in my notes, so I don't want to confuse you. But we'll come back to that alpha. So let's just stick to what we know. So this is the radius, call it R, of your Mohr circle. So R is by definition sigma 1 bar plus minus. And so let me first orient things. So sigma 3 bar is greater than sigma 2 bar, greater than sigma 1 bar. So I'm ordering, that's why I'm putting bars on top of this guy. Okay, this is not just the generic sigma 1 and the generic sigma 3. They're ordered in this form. Okay? And I'm defining plus as tension, minus as compression. And I want to note that positive sigma is in this direction. These guys are usually negative in this kind of materials. Concrete, rocks, soils, they typically have principal stresses that are compressive. They're not good in tension, these materials, okay? So if you go to the center of the earth, stuff is under compression, okay? Principal stresses are negative. So the least negative of them is sigma 3. The most negative is sigma 1. All right? So my radius equals sigma 3 bar, which is the least negative, minus sigma 1 bar. All right? Over 2. And I'm calling this point O. I'm going to call this point B. And I'm going to call this point A. Okay. Are we all right? So let's say this is minus 5, this is minus 10. So minus 5 minus 10 is positive 5 divided by 2. My radius is 2.5. All right? Okay. Now, I'm going to define this intersect here as C. And I've already defined phi. Phi, we're going to call it friction angle. just a name for now. We'll give it physical meaning later. C, we're going to call it cohesion. 1s. Again, just a name for now. Okay, so far so good? So R is also the distance from point O to point B. Then the distance from point O to point A, okay, this distance, which is this distance here, is made out of the center, or the distance from the origin to the center, or to point O, plus whatever this is. This here, by geometry, is going to be what? So I know that tangent of phi is going to be C over this. Right? So this is going to be C over tangent of phi. So this is C cotangent phi, the distance. At the same time, the center of my circle, so just like I can define R, I can define, do I define it here? Of course not. Okay, let's just write it down. So the point O is the average between sigma 3 and sigma 1. You see that? So OA is going to be minus sigma 3 bar plus sigma 1 bar over 2. Okay, and I'm putting a minus sign so I can make this positive, because this is always going to be a negative number. Plus that distance that we mentioned, C cotangent phi. Yes? Wonderful. And then by trigonometry, I also know that R, the radius, is related to this distance also trigonometrically, right? I know that sine of phi is equal to R over this distance, right? So I can write these as R sine of phi, right? And I just define R. So sigma 3 bar minus sigma 1 bar over 2, that's R. Sine phi equals minus sigma 3 bar plus sigma 1 bar also over 2 plus C times cotangent of phi. Yes, sir.
R over sine
Is it R over sine phi? Good. So sine phi equals R over that distance. So, okay, I'm having a mental block. And this is the distance I wanted. So, yeah, right. I think you're right. It's it turns out to be R over sine phi, right? Yeah, you're absolutely right, because sine phi is R over OA. Yeah, right. So, fine. So then, let's not destroy everything. Let's just write R here. R bar, sigma bar 3, sigma 1 bar over 2, and then let's fix it on the other side. So this becomes times sine phi plus C. Cotangent is cosine over sine, right? So when I multiply by sine, I just get cosine. then what do? Then I multiply everything by 2. Should have done that. Okay, so I get sigma 3 bar minus sigma 1 bar equals minus sigma 3 bar plus sigma 1 bar, right, times sine phi plus 2c cosine phi. We've been here before. What does this remind you of? At least the left-hand side. Sigma 3 bar minus sigma 1 bar should scream at you. Trust, right? It's saying that failure is achieved when the difference of these two guys is equal to something. Tresca was a simple guy and said it's equal to some constant. Right? When would you achieve Tresca here? For what value of phi, for instance? Right? For values of phi equal to 0, sine will be 0, and then this will be just 2c. So trust. Okay, so this is a generalization of a Tresca model. We'll see it in principal stresses very soon, but that's it. So, here we go. So, generalizing. So just like we generalized Tresca, remember we started with sigma 3 bar minus sigma 1 bar equals y. And then we said, okay, but let me do it for a general state of stress where I may or may not have ordered principal stresses. Let me just do it for any sigma 3 or any sigma 1, right? So generalizing to 3D, so in general, this is what happens. Sigma 3 bar minus sigma 1 bar, let me just rewrite it, less than or equal to 2c cosine phi, I'm just rewriting this, minus sigma 3 bar plus sigma 1 bar sine of phi. So this is going to become the comparison. So when this is less than or equal to that, when let's say when this is less than to that, there's no failure. I'm somewhere, say here. So let's say my radius here is smaller, but I have so say when I'm here. Say same sigma 3, smaller sigma 1. See that? So there's an infinite state of stresses that will be below the failure criteria. It's when my circle continues to expand on radius that eventually I touch failure. In fact, you can see that every isotropic state is a safe state. Sigma 1 equals sigma 3. Always nice, always a point, always here. Safe, except for when you get close to this one. We'll get there later. But for every other point to the left of the cone, right, isotropic state, safe. The moment sigma 3 and sigma 1 start to take a distance from each other, the radius starts to grow, and eventually you will fail, according to Mohr-Coulomb. Okay? Same thing for Tresca. Sigma 3 minus sigma 1 equal to 0 is an isotropic state. No problem. Always less than y, because y is always a positive part. Okay? The moment they start to grow apart, failure. Okay? In fact, here's Tresca. Right?
So that means that in 2D, Tresca and the J2 model are the same, which makes sense, right?
they're not. Why do you say that? Even in 2D, I mean, there's a difference given by phi. When phi is 0, then they're identical. Yeah.
Mhm.
But if it's not, in general, Mohr-Coulomb will give you something else. For instance, Mohr-Coulomb, let's look at these two graphs, at these two lines. The moment that Mohr-Coulomb starts to go after a certain pressure, he will predict stronger.
Yeah, but I'm saying Tresca and J2.
Tresca and J2,
And J2.
they're pretty much identical. Yeah.
That's what I'm saying.
One is it's a smooth version of the other. Yeah, and we'll map them all, and you'll see the differences. Okay, so we just rewrote this, which means that, or, when I don't know which one's which, so we were writing before sigma 3, sigma 1. I'm just going to call them now A, B, whatever these two are. Okay? It's always less than or equal to 2c cosine phi minus sigma A plus sigma B sine phi, where A, B are equal to 1, 2, 3, whatever they are. So, in no specific order, and the only condition is that A is not equal to B, obviously. Okay. So you want to look at the difference between two principal stresses, whatever they are, and you're going to look at each of them. And as long as they are less than or equal to the right-hand side, it's safe. But it turns out that you can only activate one plane. Okay, you cannot be at two planes at the same time. Okay, you always be pushing one plane. What do I mean? That if you achieve these for sigma 1, sigma 2, let's say, you cannot achieve it at the same time for sigma 1, sigma 3, or for sigma 1, for something else. See what I mean? It's only one of them. Okay. So, let's do more geometry and then you'll see it and then we'll finish. So let's just finish this. We'll graph it later. So, just like in Tresca, we'll get 6 planes. Sigma 1 minus sigma 2. So these are your possibilities. That may fail. Sigma 2 minus sigma 3 may fail. Or sigma 3 minus sigma 1. That's it. What am I doing? This is a 2. 1, 3, plus 1. So this is 2 planes. This is 2 planes. This is 2 planes. Why? Because I have an absolute value here. Okay? There is one plane for sigma 1 minus sigma 2 with a positive sign in front of it. And there is another one for minus sigma 1 minus sigma 2. So 2 planes. So it's a total of 6 planes. Just like Tresca. So speaking of Tresca, let's just do a little graph and then we'll go. So about that ruler. So principal stress. So this is sigma 1, this is sigma 2, sigma 3, as usual. Okay, the dotted lines are the negative sides of their respective principal stresses. Okay, the first yield surface that we learned was J2, circle. Okay, I'm going to test here my abilities to draw a circle here. Okay, let's see. Okay. All right, not bad. Okay, so my circle more or less goes like this. With some issues at the poles, but okay. Just like the Earth, not a perfect circle. Okay. All right, so that's J2. Then we learn Tresca, right? And Tresca, it's this. Let's see what the problem is. I didn't draw the axis the way I should have. Okay. Just straight instead of being a circle connecting the intersections with the principal axis, straight lines. These are your 6 planes from Tresca. Okay, 1, 2, 3, 1, 2, 3, 6 planes. Okay, Mohr-Coulomb keeps, let's say, it will match the compression corners of Tresca or J2, they're the same, and it will reduce, according to whatever value of phi you have, the strength in the tensile portions. Let's just do it just slightly so that we can see the difference. And then it will be straight line. So this is Mohr-Coulomb. So same compression, slightly different tension. So it plots something like this. So let's just color, finish that up. Let's put this guy, well, let's leave J2 in white. Green guys, Tresca. Sometimes I have a feeling I draw better without the wood. Okay. Like that. Exaggerating the difference so that you can see it. And then let's make this guy, orange guy, more cool. This. Now, what's the effect of phi? What do you think is the effect of phi? What should be the effect of phi? What does your intuition tell you, given what you know? You know, there's one special case.
As phi increases, gets more compact.
Right, as phi increases, this will happen. It will become a perfect triangle. So, this is phi equals 0. What other extreme do you know? No, not phi equals 0, I'm sorry. Phi equals 90. Okay, that's the very much upper case, but it's physically pretty much impossible. Okay, it won't happen. But you can approach 90, and as you approach 90, you'll get a triangle. As you approach 0, you approach Tresca. Okay, so phi controls this distance. It moves you up or down, right? Phi 90, you go flat. Phi 0, you go Tresca. Right? What do you think controls this distance? What other parameter do you have?
C.
C, right? So this distance has to be related to C. Right? And therefore, you will calibrate C just like you calibrated Y so that you match these corners for a given kappa of J2. See? So this distance, we remember we said, is kappa. That we know. This is the L2 node. Okay? And then Y, and in this case C, are related to kappa by making them coincide at the compressive coordinates. Okay? And then we let phi be whatever it's going to be, so that we can capture this difference between the compressive strength and the tensile strength of the material. Okay, and at the same time, that will also impact my pressure dependence, but we'll keep talking about that next time. Thank you.